What's up, everybody? It's Cooper and a special guest who I'll introduce in a second. I know it's been a long time, and I told everybody all the 16 people that have watched this YouTube video since the part one. I did say I was going to do the part two the next day. I did lie, it seems. But, well, we're back at it now with Physics 207. In the last video, we did the first half of this 2017 exam, which I would say this exam is probably the most technical one out of all the ones that I've done up to this point. So this, doing this one should prepare you for the other ones well enough. I've kind of fallen off doing a bunch of videos. I might do one more exam tomorrow because the exam's on Tuesday at the time I'm posting this. But the first video we did part one and question 1 and question 2. And now we're going to move on to question 3 and 4. Because, as I told you, I didn't know how to do question 4 when I first made this. But I'm here with Brooke. Say hi, Brooke.
Hi, Brooke.
Yeah, Brooke's going to do it with me. Well, we're going to do it side by side, and we'll, who cares if it's helping us study to do this? Hopefully, maybe it helps somebody else, but let's get started. Let's stop yapping. As you can see, my iPad's 1%, so hopefully it doesn't explode, but we'll get through it. Okay, so question 3. An infinitely long wire carries a current I naught sine omega t is shown, where I naught and omega are known. Nearby is a rectangular loop of wire with resistivity ρ, which has a cross-sectional area and dimensions W and H, as shown. Ignoring self-inductance, that's important, find the current that will flow in the loop. Okay, so really the best thing to do with these questions, as I'm sure you guys know, is to use the right-hand rule to find where the magnetic field is going to be going inside the loop. Because we're really just concerned with the magnetic field in this region for the most part. So let's get started. Okay, so I know you can't see me, but the right-hand rule would say that the magnetic field is going into the page through the box or this loop right here, which according to Lenz's law is going to induce a current to the left, I induced. And it's going to have its own magnetic field, but we don't need to worry about that because self-inductance is being ignored. So there we go. Let's go ahead and get our coordinate system going up. We got positive x direction. Wouldn't it be coming in out of the page right there? Right?
It's ignored.
Well, I mean, it's always good to label everything and then just kind of ignore things as you go. Yeah.
Yeah.
Okay, so we have our coordinate system.
It's like this, no?
Oh yeah. Because it's going into the page there, and then.
But the induced one is going, yeah.
Yeah. Okay. Yeah. So like, if we just for like, shits and giggles, if we were, Brooke has labeled her inducted magnetic field, which would be here, Bi, if you will.
Yeah, it's B.
It's bi. So we have our induced magnetic field there, but we don't have to worry about that because we're ignoring self-inductance. But it's always good to just kind of remember that there is another magnetic field there. But we'll say that positive x is to the right, positive y is down, just because the loop is below. And then we can say that, what is it? You curl towards x, so z would be going into the page. Yeah, that'd be good.
Wait. Yeah.
If x is here, then you
into the page.
Yeah, so the positive z direction will be into the page, and that's good because we have our magnetic field from, or we'll just call it B naught. Okay, so the law we're going to need for this question is Faraday's law, which is on the formula sheet as the surface integral of E dot dr, which equals the negative derivative of the magnetic field, the negative derivative of flux. Sorry. Okay, so that's what we have. And all this is really saying, if since last time I did the video, I was kind of just raw dogging it. We're really just saying that this equation, this Faraday's law is saying that induced voltage is equal to the negative derivative with respect to time of the changing flux of this object. So, yeah. And because this current here is changing with time, we can say this magnetic field is also changing with time. So its flux through the surface is changing. And flux is how many magnetic field lines are going through it at a certain point. So in my iPad's at 2%, so that's good. We're charging just like this wire. Okay, sorry. All right. So the first thing, okay, so we want to find the current that will flow in the loop. Okay, so we'll probably do this first. We can just kind of crack out. Oh, actually, we don't know what the magnetic field is, do we? Yeah, so another law we're going to need is Ampere's law. You find Ampere's law humorous? Yeah? Sorry. B.dr equals mu naught I enclosed. And so we need to use that to find the magnetic field that's coming from this object. So we need to find B naught. Okay, so that'd be our first step. And similar to Gauss's law, we're taking Gaussian surfaces emanating from the wire, like these circles, encapsulating more current or magnetic field lines until we have, everything. So B naught is going to end up equaling mu naught I naught we appear to be getting a call from somebody in our physics class. I'm going to pick up the phone. Hello, Sam. I'm recording a YouTube video. No, we got it, but we're trying to record the second half of 2017 and the second half of 2018 for the YouTube channel. Yeah, we started working on that this weekend too. So yeah, we'll reconvene. All right. That was another friend for our physics class. But sorry. Okay, so that's so funny. Okay, so I skipped a couple steps here, but what the most important thing is that this b can come out of the integral, and the surface integral of b.dr equates to the circumference of a circle, because that's the objects we're using to enclose magnetic field. Okay, so there we go. Cool. So we have our magnetic field. Yippee. So the next thing I guess we could do is find the negative flux, the negative derivative of flux, which is so one thing. What? Okay. One thing that can sometimes be weird about these is we do have to take a double integral here because we need area, because we're concerned with the area of which the magnetic field lines are going through. And so we have this H and W are the dimensions of the loop. So we're going to be taking a double integral so that we can kind of get all of it. So it's going to be D to D plus H in the y direction, because we chose y to be down, and then we have 0 to W in the x direction. Yeah? So, and we're going to be integrating this. So, mu naught I naught sine of omega t over 2 pi r dx dy. Oh, and by the way, it wouldn't be in terms of r, it would be in terms of y. So There we go. Perfect. And so that's going to end up being negative d dt of mu naught I naught sine omega t over 2 pi none of these are in terms of x, so those are all constants inside this first integral here. So we can just apply an x to that, and then so that would come out to be w. Yeah, and then all these terms are constant inside the second integral. So we can take those out again, and then just integrate 1 over y from d to d plus h, which is ln of d plus h over d. Okay. And then we can take the time derivative of sine, since it's the only thing that has, and so we can do chain rule. It's going to be mu naught I naught omega cosine of omega t w over 2 pi ln of d plus h over d. And that is our right-hand side of Faraday's law. The left-hand side of Faraday's law is pretty simple. All we have to do is kind of think about what self-inductance is going to be looking like. Or not self-inductance, but just induced voltage. I apologize. Is that's going to look like. This iPad is struggling, guys. It's going to be so funny if I finish this whole thing and I still have 1% left. I'm using a portable charger right now. But, okay. Ooh, yeah. So we're told that this loop of wire has a resistivity rho, right? So what we can say is using that equation for resistance, which we know from last exam is rho L over A, we can just, plug in everything that we know. So we are given rho and we're given A, which is the cross section. So the equation for resistance is the current density times the length of the wire that the current is running over divided by its cross-sectional area, which we have 2 of those things. The length of the wire that that the current's going over is this, the perimeter of this loop, which is 2h plus 2w, and that's going to be resistance. Yeah? Okay, so, perfect. So, the only thing we really need to worry about here is IR. Induced voltage is IR. It might be negative IR. Yeah, it's negative IR because we're losing voltage. Okay, so now we just set these two equal to each other and solve for I, which is I induced. So negative I induced times R equals negative mu naught I naught cosine, omega cosine omega t times W over 2 pi ln d plus h over d. Then we can just divide that r over with the negative sign, so we get I induced. You can write it down here actually. I induced equals negative mu naught I naught W cosine omega t W 2 pi ln d plus h over d. And that is the answer. Okay, and then, of course, the only other thing is that resistance is equal to, or resistance, the R, sorry, that would be coming over here. So R would be equal to, like what we said earlier, resistivity times 2W plus 2L quantity over A. All right, cool. Fantastic. Next question. This is one of the Diffie Q questions on this exam. Guaranteed. So let's take a look here. All right, let's see. Okay, so a circular loop of wire has resistance R and contains a capacitor with capacitance C. It is in the horizontal plane, and there is a constant vertical magnetic field of magnitude B naught pointing up. At times t equals 0, the loop begins to mysteriously expand. So its area is given by AT equal A naught times 1 plus gamma t, where gamma and A naught are known constants. The resistance does not change during this expansion. Find the charge of the capacitor as a function of time. Okay, so we're trying to find QT. Okay, so this is another Faraday's law question. So this is the law we're going to be using. Shout out to our TA Brian for giving us a more generalized form where you do automatically write the double integrals. I kind of agree with that more than like the regular one. Kind of implies that there's an area being taken, or it's more involved. Okay, so we need that, and then we're also ignoring self-inductance, so we need to worry about that. And I think that's all we need. We're given the magnetic field, so we don't need to use Ampere's law. Okay, so the only thing we should probably do before we start this question is we should read a little carefully here, because it says there is a constant vertical magnetic field of magnitude B naught pointing up. At time t equals 0, the loop begins to mysteriously expand. Okay, we're told that the loop is lying in the horizontal plane. So it's lying flat on the x-axis. So if it's lying flat on the x-axis, then that means x is to the right, positive x. Z is up. And then we have positive y coming out of the page. Yeah. Okay. Fantastic. Which means that really what we should say is that the magnetic field is coming towards us. I think that's a better thing to say. So the magnetic field is pointing towards us, which means that we can figure out the direction of the current in this loop using the right hand rule. So if the magnetic field is pointing out of the page, then our right hand is going to be coming up and around, and it's going to be going up out of the page, and our thumb is going to be pointing to the right. Or in other words, it's going to be going the current in the loop induced by the magnetic field at time equals 0 is going to be in this direction around the loop. And so we can say that this is I induced, and at time equals 0, when it's being created by the magnetic field, it's going to be charging the top plate of the capacitor, making the bottom plate negative. Okay, perfect. Now we can start the problem. Yeah, that looks right. Which means that the electric field on the capacitor is going to be pointing up from negative to positive. Okay. Brooke's back.
Hi, Cooper.
Hi, Brooke. Oh, look, we're at 4% now.
Wow.
We're making it. We're making a comeback.
Where do you go?
The battery.
Yeah.
So does it have a? So is I negative DQ or is it positive DQ?
Negative DQ.
Yeah. Okay. Just skip that question and let's just do this one.
I'm gonna make sure I know how to do it.
Okay, Brooke is now behind, so she's just kind of a bystander at this point.
No, I'll move on so I can help.
No.
Oh, come on. Come on. I'll do this.
We're drinking grape juice. The physics, great combo. Okay, so, I would start with the left-hand side of Faraday's law, which just kind of talks about self-inductance, and we have two things that we need to worry about.
Oh, this is the stupid one with the bee and the stupid drawing.
Yeah, it's not. Yeah, it's that. I just talked about that with them, like, kind of reading like what plane it's in, and where the magnetic field's coming out of. Yeah. So, sorry, not self-inductance. This is with self-induced voltage.
I say we whip out Faraday's law.
You're absolutely right, Brooke.
Oh, you already have it written down. Okay, I'm behind.
Brooke's a little behind. That's okay. She's still in the spirit. Okay, so this is induced voltage here, or EMF. So we have negative.
Did you write it as a double integral?
Yeah. I shout out Brian.
Aww.
Brian's our TA.
You should send the video to him.
I'll tell him I uploaded it.
Make him watch it.
I'll send him the link. All right, so we have negative IR. And now I put negatives on the IR and the capacitor because we're losing voltage over those things. So they should be negative. Our physics professor, the glorious man himself, Professor Dr. Cordell, would probably not do this. He usually goes by loops, but I found it to be a little more helpful to just kind of write negatives. Now, if we had a battery in this, you would make it positive V, because you're not losing voltage over a battery.
Wait.
But you are losing voltage over a resistor and a capacitor.
Did you do this?
No,
to figure out where I is going?
No, I did.
Oh, right.
Because it's going up into the, it's going around. Yeah.
Yeah.
Okay, so this is what we have for the left-hand side of
So
Faraday's.
This is plus and this is, no.
Yeah.
Yeah.
Because it would be going
Wait,
into
did
the...
we? I don't remember doing that for the, yeah.
So,
Yeah.
okay, guys. The next step, and I'll just write as well, the V equals IR and V equals Q over C. I should probably write those down in the exam. Okay, so the right-hand side of Faraday's law states that we need to be taking the double integral of B naught.
Wait, so why'd you say you are doing minuses?
We're doing minuses on the left-hand side of Faraday's law because we lose voltage over resistors and a capacitor.
Is that something we know?
Well, another thing you could do is make a loop, but I feel like for induced voltage, we're more concerned about what we're losing voltage over when the current is being drawn over those things. Because really this I right here is induced current over the resistor.
But how do we know we're losing?
Because you lose, when you go over a resistor, it's a voltage drop. And you voltage drop across your capacitor.
Oh, and there's like a resistance.
Yeah, so the wire itself, the loop of wire, has an inherent resistance R.
I see.
Okay. So, the right-hand side of Faraday's law, which is going to be equal to this, we can come out to be... Well, okay, so we're given an area that changes with respect to time. And since this double integral dot ds is supposed to signify or symbolize an area like we did in this problem with the loop, we can just go ahead and say that we have the negative time derivative of B naught times the area, which we know is A naught times 1 plus gamma t. And then we take the derivative, and we'll end up getting negative B naught A naught gamma. Jinx. All right, we get that. So
And then
now we set this equal to the right hand side. Oh, one more thing that we need to write down is that charge is the derivative, or that current is the derivative of charge.
wait, current. Oh,
The
I
the dq.
equals dqt dt.
dq dt.
dqt.
dqt. dq of t. Is that what you're saying? Yeah, Brooke's right. You should usually write dqt. That's
dt.
dq of d dt. Yeah, because really what we're what we're trying to find is qt, because we're trying to find charge in the capacitor as a function of time. This is something our TA Brian has also given us a little bit of insight on. Yeah. Okay. So let's get this in the bag. Okay. So we have, and I'm going to use this. I'm going to when we're setting these equal to each other, I'm going to plug in I equals dq dt to that. So we have negative dq dt of r of times r minus 1 over c times r, or q, sorry.
Wait, what?
Equals negative b naught a naught gamma.
Then you find the homo
Yes.
equation.
We have to bust out some differential equations real quick, guys. So go ahead and let's go ahead and change all these to positives. Yeah. Since they're all negative, we can just multiply it by -1. Doesn't change the function. And so we have to solve the homogeneous or homo differential equation.
By setting.
Because this is a first order linear differential equation. And so we can set the left hand side
equal to 0.
Equal to 0. Exactly. And then solve for dq dt. dq dt equals negative 1 over rc qt. Okay, cool. The general form for the homogeneous or homo equation is A, or alpha, e to the negative beta t. And then dqh dt is negative A beta e to the negative beta t. But we know that beta... Now, as Dr. Cordell, I apologize, Dr. Cordell would say, diffie-q is not a prereq for this course. And therefore, I'm not going to explain why I know this, but beta equals 1 over RC. And so, usually for these questions, you can just automatically say this is beta right here. The coefficient of QT is beta in this equation, when we solve for dq dt. So that's going to go here. And so we end up getting the dq dh is negative A over RC, e to the negative beta t. Negative 1 over RC, or negative t over RC. Okay, cool. Now we plug this value into here to solve the non-homo differential equation. So we bring that back down here. So we get dq dt, we get r times negative A RC. Now we're solving for A. Negative t over RC plus 1 over c q of t equal to b naught a naught gamma. Now we're going to set all the t's in this function equal to 0 so we can solve for A using the initial conditions. So this will go to 1. This will be 0 because q of 0 is 0. Because before time equals 0, or at time equals 0, the loop starts growing and the flux starts changing, which induces a current in the wire. But before that current's induced at time equals 0, there is no charge in the capacitor, so Q0 equals 0. The R's, The r's cancel. And so we're left with negative a over c equals b naught a naught gamma. And so a ends up equaling negative c b naught a naught, or a naught gamma. And then we plug that back into this, and so we get that the c's would cancel, so we would have b naught a naught gamma negative t to the r over rc. Sorry, I forgot to write the gamma. Plus 1 over c q of t equals b naught a naught gamma. Solve for c, get qt, we get b naught a naught gamma minus b naught a naught gamma e to the negative t over rc. And that is our final answer.
Did you get minus?
Yeah.
I got plus.
Did you get that a is negative? Negative c?
Yeah. I don't know. My math always gets funky.
Well, that, so a was negative, and then you plug that back into this equation.
Oh, I can't. Yeah. Yeah, no, it is.
And then that a, that should be negative, negative, positive, and then you bring it over to the left, right?
Yeah.
Or to the right.
So it's negative.
Yeah, that's not bad. Okay. All right, guys. So that is the second half of 2017, like I promised you. Sorry it took me over a week. It was Passover. You know, you gotta take a chill pill. And it's Easter.
It is Easter.
Yeah.
Happy Easter.
Happy Easter, Brooke.
Oh, thanks.
Aw. Oh, thanks. All right, guys. So, we're gonna do the second half of 2018 as well.
Right now?
Yeah, why not?
Okay.
It shouldn't be that bad. Let's
Right into it?
Yeah, let's just jump into it right now. Okay,
Wait,
so
I don't know if I have this downloaded.
you should. We were just doing it.
I do.
2018, guys, is kind of annoying, but
Well, question 2 is a little.
question 2 is a little goofy, but we don't care. We do care, but we don't. We do. Sorry.
So do we?
I don't know. Okay, so part 2 of 2018. So sorry to. You guys can do this on your own. I don't want you.
It's not too bad.
Yeah, it's not bad. It's not bad. It's not bad.
You can figure it out.
Yeah, you can figure it out. All right, so. Do you need 2018 up here?
The answers?
I'm going to have the question up here as well.
Oh, okay.
We currently have the exams projected onto my TV screen, and we've been just grinding them out.
Yeah.
Just going nutso on these exams. All right. So.
I think it'd be funny if I worked at a exam
And put on the YouTube video.
and try to explain it to the.
Do you want to do it?
To the. This
Do you want to do
one?
this one?
This one?
Or do you want to do this one?
Ooh.
That's gonna be rough. But we're gonna get through it, guys.
I feel like okay. I don't think circuits are that bad.
You don't think these circuit ones are that bad?
Like, I don't know if I'm like an electrical engineer, Albert Einstein.
Yeah.
Like, they're not horrible.
These circuits one? Do you want to do that one for us then?
Or should I mean, we should start with, 3. We should do it in order.
Okay. Brooke's gonna do the last question apparently.
Well, what if I want to do this one?
But I thought you said circuits aren't bad.
Alright, guys. Welcome back to the YouTube. Today, we will be working out, don't panic, exam 3, 2018, question 3 and 4. Second half of 2018.
Yeah, because we did the first half before the video. Then we went to Roadhouse and got a steak because we were hungry. But now we're back and we're locked in. Okay, so
there's a rod of length H
yeah.
with resistance R, and it can slide without friction.
Okay.
There's a magnetic field B naught
Let me label this. Okay.
that is pointing into the page. That's what the X's mean.
Okay.
I don't know. It's by convention.
By convention, she says. Okay.
A battery is connected to the rails.
Oh man, a battery.
A battery with
Let's see what-
voltage V.
Okay.
It appears. If the rod is at rest, what will be the magnetic force on it? Okay, so that's one question. This seems like a two-parter.
It absolutely is, Brooke. I see a 3A and 3B on the answer sheet.
Well, we're not looking at the answer sheet.
Yeah, we actually, I've never
I see 2 question marks
I've never seen this in my life.
in the paragraph.
Okay.
Batteries? Okay, wait, where am I? Oh, yeah, so we have to find the magnetic force if it's at rest. And with a constant velocity, would you have to pull or push the rod in order to make the magnetic force on it be 0? Okay, great question. So,
Yeah.
wait, should we switch iPads?
We can.
So I'm
Okay,
doing it.
Brooke is now doing the question. Okay, I'm doing it on her iPad. This is such a tiny iPad.
Okay.
Your freaking iPad's at 28%. Dang it. It's gonna die on me.
So there's not only is there a current from the battery, but there's an induced current from the magnetic field. Would you say? Or is the battery right? Because there's a not only because
Yeah?
oh, okay, you drew it the same way as me. Okay, right hand rule. If the magnetic field is going in, then the current's, this way. The thumb's going to the
Yeah, it's going,
right.
Yeah, because it's going, you could point your straight fingers in there. Like that.
Okay.
Like into the page.
Yeah.
And then you can curl it.
Wait, what happened?
Dr. Cordell always does,
Oh.
he always does into the page and then he curls around the wire.
Okay.
He's very dramatic with it too.
So
Emphasizes
that's
it.
only the induced. There's not 2 currents. There's
I mean, it so happens that the battery's current is most likely going the same direction as the current induced by the.
Yeah.
So I mean, there is a current coming off the battery.
Okay.
But okay, so we need so in order to find.
Is this my question or your question?
Oh, that's a good point. Sorry.
So.
What do we need to do first, Brick?
Well, we need to find the magnetic field, or I'm gonna say that we need like Faraday's law.
I would agree.
So let's write down Faraday's law. We should have this, on the formula sheet.
We have this on lock.
Got it on lock. It's this E.dr closed integral thing of sorts in which, and then a negative d dt. I like how your iPad feels.
What like how?
Like it's like
the
you
drawing on it?
Do you have like a paper
Yeah.
screen protector of sorts?
You can kind of feel it. It's older now, but yeah.
Well, I like it. It's like paper. Okay.
That's the point. It's game changing.
And then, do we also need that one? The one. Yeah.
Which one? This one?
No.
Or that one?
That one.
Ampere's law? No,
Yeah,
because we're not. We don't need Ampere's law because we're given beta naught.
All right, never mind. No Ampere's law. Oh yeah, magnetic field is just beta naught.
Yeah.
Yeah.
Which is very nice. I'd say we don't need no Ampere's law. Okay,
So I want to say that we're gonna need a double integral, but so we have this h here. But I feel like we need a. How does this work?
Okay, so let's finish writing down all the laws we need.
Of course.
Because we don't. Not only do we need.
How does this work?
What? Oh, you click one of these, and then you double tap like yours. It'll go between eraser and whichever pin you have.
But how do I get this out of my way?
Yeah.
Fair enough.
Yeah, the more you know. Okay, so Brooke has said that we need. Faraday's law, which is the which is what I'm writing down. Or, sorry, you can't even see what I'm writing anymore. I forgot. And then we also need the.
I'm gonna write it down.
Probably need the force equation on the rod, which since the rod is essentially a current carrying rod, we're going to need dF equals I integral dot ds cross b.
Wait, where are you seeing this?
That's okay. So for some, we're not given that in formula sheet,
Oh.
but we're given force QV. And that's what I don't understand is why we're given the point charge version and not the
So this is
wire one.
given.
Yeah. That's when we probably might need to memorize, like, just kind of.
And then we derive this DSXB formula of sorts.
Yeah. Because if you remember, I is dq dt. It might have something to do with it. But anyway, that's besides the point. So, let's see. So I'm going to go ahead and get the left-hand side of Faraday's out of the way. Dot dr. Because we know that batteries connected to the rails.
Should we draw a loop?
So we have V minus IR. Okay.
That's on the loop?
Yeah, it would be going
Down.
down. Yeah,
Can I see something real quick?
sure.
Oh. Never mind. Never mind.
Okay, so
So I'm going to draw the loop like this way.
I'm just doing V minus IR, personally.
Oh, yeah. I mean, my loop would be the opposite, which would be IR minus... Yeah, I'll just do V minus IR. Forget that I drew that. Yeah. Because it's decreasing the voltage.
Yeah.
Right? Yeah.
I'm going to say that X equals 0 is where the battery's at, and so I'm going to say that X is in this positive right direction here, and that Z's into the page, and Y is going down. I want Z to be going in the same direction as the magnetic field. Okay, so let's continue on. Okay, so I'm gonna go ahead and just say that from 0 to X.
So is this your problem now?
Oh, I apologize. Please continue.
Okay. So we're going to hit it with a double integral.
Yeah.
So from, 0 to X. And then, I'm having thoughts, feelings, and emotions. 0 to H, would you say that's fair?
I think so.
Of this B naught, which is just B
Be
naught.
not afraid.
Right, of course. It's just B naught. It's not like, equate. Okay. B naught. And we need a DS.
Yeah.
Oh, which is, you have to do the thingy of integration for so it's going to be dy dx.
Precisely.
That's what, like Calc 3 or something? Cal 1 knowledge even?
Maybe.
Because you need what's it called? It's a thing of integration. It's a constant of, no.
The limits?
No, this thing.
Oh, like, what do you mean, like the...
There's like a term for it, no? Variable of integration? I don't know. Besides, it doesn't matter.
It don't matter.
Alrighty, let's
You
solve.
shouldn't be in this class if you haven't done calculus anyway. Okay, so one other thing we could probably do is determine the direction of the force right now on the rod, because we know the current is going down.
Oh, and you use this fib rule of sorts where F is the thumb.
Force is the thumb.
Current is the index finger of your right hand.
Your right hand, all your right hand. And then B, magnetic field, is your middle finger.
So the B's going in.
Yeah, B's going into the page.
I's going this way. So force is going like
To the right.
up. Oh, what?
Well, if B's going into the page,
Yeah.
current's going down the rod.
Wait, current.
Like
Oh,
this.
of the
And
rod.
then,
Of the rod, guys.
yeah, we're worried about the rod. So force is to the right.
Yeah. To the right.
Okay, so we can put a little vector there for force.
Are you drawing that? Oh.
Just to the right.
I mean.
Okay. All right. So the next thing.
That's where the F is. So we gotta solve this. Okay, someone already solved the integral. It's fine. On the other iPad. So you're gonna do negative d dt of, b naught h x. And we know that the derivative of x, or position, is velocity.
Oh my lord.
Oh, okay.
I see you drew an arrow, like I did.
H, and then this v of sorts is velocity. So then let's set the two hand sides of the thing equal to each other. V equals, no. How do I get the, oh.
So one concept that I feel like we didn't really cover much in class is magnetic force. And
okay.
I asked a question the other day to somebody, and I was told that when current is 0, I think force is also 0.
I mean, it makes sense, right?
Force is 0.
Well, because aren't they cross product? Like, these three things are, no?
I'm not sure. I don't know if it has something to do with that. Maybe.
Oh.
It might.
Well, because if something's 0 and you try to multiply it by something else, it's going to be 0.
Yeah, so it's just kind of implied that if current's 0, then force is 0.
I do not remember hearing that come out of Dr. Professor Cordell's mouth.
Yeah, I don't think we will necessarily be tested on this that much, but it is nice to know. But so part A is asking for the force on the object.
And if the force... Oh, wait.
If the rod is 0...
Wait, what's it asking? If the rod is at rest, what will be the magnetic force on it? So there's no current? Oh,
so
never mind. Don't listen to me.
What I think So this question's a little weird. You might not necessarily need Faraday's laws so much for this. You do for the second part, but it's good to kind of get all this out. So part A is asking, what would the force on the rod be, or what would the magnetic force on the rod be if it's at rest? So if the rod is at rest, what will be the magnetic force on it? So...
Oh, well, the velocity would be 0, no? Never mind. Wait.
And in the equation for this second one, this first one there, this df equation. Sorry, it's just f. F equals this. I apologize. There's a little bit of lag between your drawing thing and...
No, it's because I have it as soon as you erase something, immediately goes back to the pen, so you don't have to double tap. So, like, erase something and then immediately goes back to the pen.
Okay, that's kind of nice, I guess.
So as soon as you erase something, it's immediately pen, so you don't have to double tap again.
This is kind of just become us just yapping. No one's gonna watch this video. They're like, "This is horrible." Horrible.
So, on the other iPad, this equation.
F.
Oh, it's just F.
It's just F because I put the integral in there. Yeah.
I see.
So it's F. If the magnitude F the vector F force vector equals I times the derivative of ds, and integral of ds, and that integral is over the rod. It's the length of the rod. So we can say then that we have I times the integral from 0 to h ds cross B, which we can say is
Wait, hold on. I'm getting a little lost right now. Wait. So
that integral is over the rod's
over
length.
the rod. Oh, you're taking like little bits and pieces of it?
Yeah.
I see.
And because the force and current are perpendicular, because the current, the direction of current is ds. So ds is over the rod's length.
So are you taking like little y's?
Little i's, yeah.
No, little y's.
I mean, you could, but like it's just. I mean, ds could technically be dy.
dy because it's like the.
Brooke does make a good point. It is dy technically.
I see. The one thing about this physics is I hate ds. I don't know what this s.
Yeah, well, it's good to. Brooke makes a good point. Putting it in terms of the coordinate system that we chose is a great idea. So, current times the derivative with respect to times the integral with respect to y, cross b. The magnetic field is perpendicular to ds or dy. This is dy. And so dy is going down and magnetic field is going straight into the page. So dy and z are perpendicular to each other. So that means we can use this concept for cross products, which is b vector cross a vector equals a times b sine theta.
Wait, a cross b equals.
The magnitude of a times the magnitude of b times sine. Times the angle between them.
Which is what, 90?
Yeah, and since
In
they're
theory.
and since they're perpendicular, this would just be 1. And so, in our situation, dy cross b are
Is
perpendicular, so we can just say it's
1.
dy times b. And so,
I did something. Okay, never mind.
the integral
Sorry.
from 0 to h dy is h. Comes out to be h, because you're just adding a y here and evaluating it from h to 0, or 0 to h.
Okay.
And then we're multiplying it by beta naught, or b naught. Okay. Cool. So now we have our force. And
This is force. This is literally just the answer for force.
This is the answer for force. And
So
we know that it's to the right. So we can just draw this little arrow here. To right. And we know that from the right-hand rule. Again, current is your index finger pointing down. Magnetic field is your middle finger going into the page. And your force is your thumb pointing to the right.
Yeah.
Okay, part B.
But they wrote I. Do you have this?
Yeah, I, H, B, naught.
No, but then they have I equals V over R. Oh, that's just V equals IR.
Yeah.
Bruh. Okay, do you have to write?
I
Oh.
think so.
I'll write that up here. V equals IR. Nope. IR.
Yeah, I'll write that too.
Wait, the pen got bigger. Hold on.
Yeah. You want the pin point.
Oh, I chose the wrong.
Click
It's too big. Oh.
It's the smallest size.
Do you see how it's bigger though?
The harder you push on this one, the more ink comes out. I think. I might be lying.
Okay.
All right. So
doesn't matter.
anyway,
Part B.
Part B says, with what constant velocity would you have to pull or push the rod along the rails in order to make the magnetic force on it be 0? So this is where the concept that I equals 0 implies that force equals 0. So we want the force to be 0 now. Yeah.
Oh, okay. Yeah.
So
should I rewrite the equation of this up here that I didn't use?
So this is where we would use Faraday's law. V minus IR for the left-hand side equals negative B
That we literally wrote up there.
H.
That it's fine. Says point.
H velocity. And as I stated earlier, force is 0 when I equals 0.
How do I go back? It's fine. I shall erase and rewrite. Yes, F equals 0 when
current equals 0. Now, I wish I could explain. I mean, I'm sure the textbook could tell us why that is, but I don't think anybody's interested in me whipping out the textbook right now to figure out why it's. Yeah, so we'll just go with it. I don't remember us being taught that though.
Nope.
Now that's no we have been a little distracted in class with other assignments and just life in general. So no slander.
Yeah, and it's during the lunch hour, our class.
Oh, yeah, we're quite
so
hungry.
Sometimes we get a little hangry.
Sometimes I'm thinking about lunch.
Yeah.
Okay, anyway, so 460 current user. So we're gonna use the Faraday's law equation, and so we can just go ahead and set I equals 0.
Perfect. So V
Equals
negative B not HV.
Yeah.
And the V is this velocity. The V and this V and this V are not the same.
Yeah, that's velocity.
This is voltage. This is velocity. Hopefully you can tell with my handwriting difference.
So we can just go ahead and
Right?
velocity. Yeah, put a little like fancy curve on the V. Capital V.
So this V is what we're solving for.
Yeah.
Equals V voltage.
Yeah.
Wait. But theirs is positive.
Ooh. I remember a friend of ours, I haven't asked for the consent to be put in the video, he said that we want it to be in the opposite direction. So each multiplied by -1.
Oh, is this Lenz's law?
I think it is, but maybe. I don't know.
Don't quote me on that.
But the velocity is to the right.
So it's positive.
So, yeah.
Positive.
And honestly, if you get a sign difference, that's not too much of a point off, I would say.
Because the goal is 20 out of 25.
That's true. That's an 80
That's an 80.
on the exam.
And that's great, honestly.
Great.
Great.
All right, guys. So that's the third question. Brooke did a fantastic job, I would say. I hope you're all clapping for her right now.
Thanks, guys.
Did you box your answers?
Oh, always.
There you go. Beautiful.
Boom. Oh, I cut that off.
What do I always say?
I don't remember.
Boom shakalaka.
Boom shakalaka. All right, next question. The circuit below.
Oh, you're doing this one too? You got this in the bag?
Always. Okay. I think I understand circuits.
All right, you understand circuits, guys. Let's.
And also,
I believe in you.
don't quote me on
I
this.
believe you. Okay.
Question 4. I know a thing or two about question 4.
What do you know about question 4, bro?
Before even reading the question,
Already making assumptions here?
I'm making assumptions.
Oh no. She's making an assumption, guys. I'm terrified. I'm worried. I'm so scared. Oh, she's writing Faraday's law. What? Okay, so
Faraday's law.
E. Dot D.
Would you agree though?
Oh, absolutely.
Okay.
Without a question.
And also, I'm gonna write a little note. I think I'm gonna change the color.
We should change the color. I don't do that for y'all. Y'all better respect this. This is huge for the program. I post the video in black and white anyway.
No.
Diffie Q, yay.
Okay, do you agree though that
I do.
that we're gonna have to do some differential equations? We're gonna actually derive the entire thing as one would do in a differential equations class.
Okay, so.
Oh, you didn't like that joke.
No, I agree. Absolutely.
Okay.
It's just, it's almost midnight. I'm tired.
Oh.
That steak filled me up.
Good.
All right. So, let's do this. So, we have that a circuit below was put together a long time ago. Well, that rhymes. Wow.
Does it?
A circuit below
Oh,
was put together a long time ago.
It's a riddle.
We're cooked. It's during the exam. I'm like, oh, that rhymes. Really loud. You hear me across the room. With the switch in position A. Okay, so it's at position A.
So it's like actually down.
Yeah. So.
So this is a closed.
So that the steady state was reached.
Mm.
Ooh, this is important.
That is important.
At time equals 0, the switch is moved to position B. Okay, find the charge of capacitor as a function of time for t greater than 0. Okay, so ignoring self-inductance. Oh, man. Okay, so what I think is that if the switch is at A and it's moved to steady state,
then there's current flowing. The capacitor is...
It's a steady state, and there's a capacitor. So there is no current.
But there's charge built up on the capacitor.
Yeah, see,
yup.
Gotta remember exam 2 stuff. Yeah.
But I always put the I.
Well, okay, Brooke is right. There, you would have had an I going around this direction, going away from the positive of the battery, and it would be traveling along over the resistor onto the positive plate.
So we don't have to find the before, right? That's like irrelevant, is it? Because
so
let's find the after as it's discharging.
Yeah. So what we need from the right side of the capacitor is the t equals 0 charge on the capacitor. I think. So. So if we have E. If we have the left hand, okay, so let's do t equals 0. So t equals 0. We have the left hand side of Faraday's law, E dot dr equals V minus IR minus Q over C. Yeah?
Yeah, Q over C. I agree.
Okay, so I just want to make sure that we're not leading anybody astray. I did this question a long time ago, I think. I feel like I did. Maybe I didn't. Perhaps I'm lying to everybody right now. I would hate to. I remember doing this question I did with that guy from our class. Here it is, so we can reference this. I'm gonna get up and turn on the light because I can't see.
So,
Do you see? No? Okay.
Yeah.
So, what we need first is that the left-hand side of Faraday's law.
No IR.
Oh yeah, there's no IR
because it's steady state. Yeah.
Current 0.
Yeah.
So
sorry, guys.
Yeah, I equals 0. I was wondering that because that would be like a really advanced differential equation if it wasn't I equals 0, which means that we just have V minus Q over C. And remember that's QT, yeah? Really Q of 0 because we're evaluating this at 0.
Yeah.
And so that equals 0. And the reason it equals 0 is because the right-hand side of Faraday's law, because we don't have an external B field anywhere, and we're ignoring self-inductance.
There's no current.
There's no magnetic field anywhere. So the right-hand side of Faraday's law is 0.
I'm just going to keep this as, I guess.
And so we get that V, or we get that Q0, or the initial condition, I guess.
Equals CV.
Or the charge on the capacitor at time equals 0 is what I should say.
The charge on the capacitor at time equals 0.
Is VC. Right?
I put CV. Same difference.
Let's stick with each other. Here's CV.
CV.
I'll write CV.
Okay.
Like you did. So, what we just did there, and I did. You got it back. So, what we just found there, guys, is that we're using that. So, this right-hand side of the circuit. Right-hand side of the circuit is, like an exam 2 circuit.
That was a pretty good circle I just drew.
I agree. Good thing we got it on video. So the right-hand side is like a circuit from exam 2, and so you solve it like that. but just using Faraday's law instead of,
Yeah.
Anyway, so
But as soon as t is greater than 0.
yeah, so now we need to get involved with t greater than 0. So time greater than 0. So at time t equals 0, the switch is flipped to B, which means that the battery no longer has anything going on.
Boom. That goes away. Bah.
Yeah, battery's practically gone. You can just scribble it out, I would say. Right?
Sure, yeah.
So
Because it's not closed. It's, it's going like
yeah,
that.
perfect.
Yeah.
That's what I was going to do.
Did you draw it that way? Do you like... We can draw it a different way.
No, that's beautiful.
Well, I don't like my arrow. It looks weird.
So at time t equals 0, the switch is flipped to B, which gets rid of the battery, essentially. And now the charge is going to be coming off the positive plate of the capacitor. Come on, man. Come on, man. Come on.
Yeah.
You want to draw the new current for our viewers back home? Would it be?
What?
Would it be going that way?
Oh.
Would it be going? Yeah, it would be going this way, right?
Yeah, sorry. I was on autopilot.
It's okay. Yeah, it's the best of us.
Because it's always from the positive.
Yeah.
As a convention.
I love convention. Do you like convention?
Yeah.
Big convention guy.
Okay.
Okay, so now we have a new thing for the left-hand side of Faraday's law, which I would say is it's negative Q over C minus I R1 minus I R2, which we can write as negative Q over C minus I times R1 plus R2, since that's the same I.
Yeah.
So
if you really want to get technical with it.
And then I is going to be equal to negative dq dt this time because the capacitor is losing charge. It's discharging over the circuit. Because we built it up with the battery. It's losing charge. And now it's losing charge.
I equals negative dq of t.
dq of t, correct.
dt.
Good catch. dq of t over dt. Okay, now the right
and this is where it gets a little...
It's a little freaky.
Intense.
That's a little intense.
Because you can't solve this thing, or this, when you set it equal to this. No, that's not what we're doing. No, we're... Okay, don't listen to me.
No.
We have to do the other side of Faraday's,
Everyone
right?
take a breath.
We have to do this. We have to do this. Oh, shoot. Okay, we have to do this, right?
Correct.
Okay.
So, the right-hand side of Faraday's law is...
Getting ahead of myself. I apologize to the viewers back at home.
So...
Wait, it's negative D...
Ooh, guys. This is huge.
What's huge?
The right-hand side is still 0.
Oh.
Because we're ignoring self-inductance.
We're ignoring self-inductance.
And there is no external... So there is no external...
Wow.
I'll write this here. No external...
Should I write it?
You can, yeah. External B. No self-induced B. That's what I wrote, see.
I heard you. You said it out loud.
You right. Anyway, so that means the left-hand side is going to just set equal to 0. So we can have... So I'm going to write that we have negative...
I'm going to write it again because...
Negative dq dt.
Oh. Whoa.
Yeah.
Got me there. I just wrote I.
Calm down. Calm down there. No one's going to watch this video. We're cooking.
Wait, so would it be plus? Because I is negative? You see what I'm saying?
I don't think so.
You flipped your... Oh.
Well...
You flipped it.
Did I? It's definitely negative dq dt. Yeah.
Yeah, but it's also minus. Did we do that right?
Maybe it's negative q over... Maybe it's positive q over c.
Well...
No, that won't make sense.
Well, because the electrons are moving that way, right?
Yeah.
So it's the opposite, so it'd be positive, no?
But I thought it was because it's losing voltage over the capacitor.
Oh. So
Well,
I don't.
Let's just go with it. So since they're both negative, let's just see what we get. And if we get the signs wrong, that'll answer the question.
Yeah.
Right.
And then we can explain it.
Yeah. Okay. So.
Wait. So what are we doing? Both of them positive?
Yeah.
All right.
Well, they're negative here, so we can just, and since we're setting equal to 0, we can just multiply everything by -1.
Yeah.
All right. So now we can solve with differential equations. So this is a homogeneous DQ. Whatever.
Equals 0.
And equals 0. So we can just solve it.
And we don't even have to create the homo.
We don't have to do anything.
This is an easy one.
Yeah.
Dare I say? Well, I don't want to get,
Well, let's not too cocky.
I don't want to say it's easy, but
Yeah.
I'm sorry, guys. Okay. So
We
do you?
apologize. They don't care.
Well, I hate when people say it's easy, and I'm like, I have no idea what's happening.
Yeah.
You know what I'm saying?
Yeah, that's a pet peeve of mine, honestly.
Oh.
Well, no, I'm agreeing with you. I'm agreeing with her, okay? Not because you said it, but I'm agreeing. Like, when people say, like, oh, it's so easy. Like, okay, explain it then.
So it's like that?
That's my favorite thing to say to people, like, especially engineers. Explain it then. Because I know I couldn't. I don't know. Right,
Yeah.
okay.
Yeah.
Just kidding to the engineers out there that watch this video. All right. So, we do need the general form still for the D. So
I'm having thoughts, feelings, and emotions. I'm thinking that we have a beta among us.
what are you trying to say? What are you trying to say, Brooke?
I apologize to those viewers of my handwriting and or the
I'm sure they appreciate your handwriting.
clarity of my. Well, I feel like my work gets like messy. It's not like easy to keep track of.
Well, that's what we're here for, to explain why things are getting.
Do you think this is my beta?
What are you talking about? Yeah, that's beta. That's what it would be.
Or do not disturb turned on?
It do be midnight. Hope you guys had a good Easter.
Yeah,
It's now the 21st
of April.
That's crazy. It's
Scary.
scary.
Do you know what that means, Cooper?
What does it mean?
It means the exam is tomorrow. Oh
boy. That means the final's in 4 days. Oh boy. Not the final.
The
comprehensive exam. That's propaganda. You can't call it the final. Okay.
Wait. So this is Q of T, right?
Yeah.
I don't like how I wrote that. I'm gonna rewrite that. Q of T.
Mm-hmm.
You're going all blinkers. Oh, you already did your dq dt. So then we take the derivative of this. So to those who have not taken differential equations, I'm sorry that you don't have that knowledge yet. It's really enlightening.
Who are you talking to?
The viewers.
Oh, the viewers haven't taken DiffEQ?
Yeah. Because honestly, it was such an...
Did you take DiffEQ?
No.
Okay, so that R1 cancels out. Oh, and we're also
I'm going to need you to look at this because I always mess up the differential equation, actually, and I don't want the viewers to be, like, looking at this and being like, I'm going to put my T on top. I see that happen sometimes. I feel like it's, sometimes easier to see what's happening. Is that how you do it? It's negative. Okay. Yeah. You know what? Yeah. I want to make sure I'm doing it right for these lovely creatures that are
watching our YouTube video.
Wanting to be enlightened of the
physics.
2018 exam 3 question 4. differential equation derivation.
You know, it was 6 years. You know, it was 6 years before 2018.
2012.
2012.
It was a great year for the Olympics.
Great year for the Olympics. Did you see the Olympics thing?
So then what we do is we plug this. Here, I'm gonna do a little highlight moment. I'm getting fancy with this. Purple. Let's do purple. Changing your highlighter colors. Sorry about that. I'm gonna plug this into here, and we're gonna solve for this. Okay, Cooper, what is going on with your arrows?
That's an aggressive highlighter you got going on there. Purple's a crazy color.
It's to, really highlight the math.
The math.
So QT over C. You know what? No. Yes equals. So this point is just calc.
Correct. Or algebra, really.
Multiply by C. Oh no. You know what, guys? I'm going to set T equal to 0. Do you do that?
Yes.
Okay. T equals 0. I'm scared I'm gonna need more space. Also write small. Is Q of 0 0?
Usually it is, but remember.
But in this case,
with
it's
this, yeah, we found Q0
Oh,
for A.
y'all, this is going crazy. So I don't know if you see if this is Q is 0.
That's the charge in the capacitor at time equals 0.
So then it's just V because this cancels out like that.
Correct.
Right? You see that? Do you understand what
I do understand.
Okay.
Beautiful.
So V equals A over R1 plus R2. And then C, because this will go to 0. What am I solving for? Oh, I'm solving for A. This isn't too bad. A equals VC R1 plus R2. Is that what you got?
Mm-hmm.
Oh, that's awesome. Oh, and then you plug it back into the thing.
The original equation. Yeah. Beautiful.
Do I plug that A in here? And this is for no. Q T over C plus. This thing. This, yes. Wait. Let me see if I can do this because I am also taking this exam.
Are you? I wasn't aware. I thought you were doing this for fun.
Shout out to whoever is still watching.
Yeah. You know, I can see how long people, on average, watch the video.
Really?
And I never get, more than 30 seconds.
Really?
Well, I mean, I think people, skip around to the questions they need.
I may or may not be lost in my own work. Which is okay, that happens sometimes, but all you can do is try. So, Q a T.
So, let me see where you're at. So, that's the original equation that we're plugging everything we get into.
Yeah.
This
And
thing.
that's
Here,
what, and that's
put
where
a
I'm.
star next to it. just so people can see where you're thinking, if they did watch the video. Which I doubt anybody's watching it. But it's good for us. This is good for us. So you're solving for that.
Yeah.
So that C would cancel with that C. The R
Well,
would cancel.
I'm gonna like take this all over here. This.
I believe you have one extra R1 plus R2 on accident. That's not that.
Right here.
Yeah, but that's.
Ooh.
Ooh, your A is wrong.
My A's wrong?
Yeah.
No.
It is.
No. Boo.
Grape. Not grape, but will be grape. Okay, so
Bless you.
A is CV.
What in the? Huh?
So when T equals 0.
Okay, guys, we're moving back up here.
When we're solving for so this is.
I didn't mean to erase that.
So when we're setting T equals 0, we're setting that equation with the star.
Yeah.
Equals 0.
That equals.
But you're missing the coefficient R1 plus R2. So that shouldn't be there. Shouldn't be.
Huh?
So when you plug this value for
so then there needs to be another one.
Yep. Yeah.
Which cancels out here.
Yeah, put like parentheses around all of it. Since like right here. In between there you go. Perfect. So then
everyone knows how great I am at calculus.
So V equals for C. This is algebra. We've done no calculus. So that's just BC. Yeah.
So
Perfect.
then this goes away.
Yeah.
No.
Yeah.
No.
Yeah, they said equal to 0. Because no, you have that R1 plus R2 right here. Well, your A used to be C.
So
you could erase that and put it out there if you wanted to.
Let's get rid of this. I missed it. All right. Okay. And then
Put the parentheses.
Parentheses.
R1 plus R2 equal to 0. Okay.
Boom.
So now you can cross everything out and solve for Q.
So that goes away. That goes away.
The C's cancel.
That.
Perfect.
Okay, I'm gonna write this a little lower just for like visual purposes. Q of T equals V. What?
Positive.
What?
Because you're adding it over to the side.
Alrighty, CVE to the negative T over C.
You're looking up a lot. Yo, we should make one of these videos like super wasted. Just trying our best to do one of these exams.
That sounds illegal.
I'm joking.
I'm joking. Okay.
We wouldn't do that. We're good people. We celebrated Easter this year and passive. All right, guys.
So this is what Q of T equals.
This video is gonna be like an hour and a half long. This is gonna be impossible. Okay, guys. So, boom shakalaka.
Brooper out. We'll
you.
catch you on the flip side.
Thank you for watching our video. Let's do some shout outs. We have shout outs to Brooke for doing 2 problems with us and showing us the simplicity of circuits.
You're too kind.
Shout out to Brian.
The one and only.
For final, what would you call it? What would you say? Like
He's our TA.
Well, he's our TA, but he like.
You know what, Brian? I hope you are out there watching this video.
Me too. You taught me everything I knew about physics, and Brian like he like took what Cordell said and like really made it concrete.
Yeah,
he recitationed our he recited.
Yeah.
The physics.
I know what you're saying.
Shout out to.
I'm not done with this Brian thing.
Okay,
I hope, Brian, that you are out there floating on this planet, either eating a whole Costco chicken.
I think it's an HEB chicken.
Oh, HEB.
I think it's HEB.
Rotisserie chicken.
Because he shops at HEB, we shop at.
Oh my gosh. And or a deep dish pizza.
Yeah, I hope he brings a chicken to the exam.
Or a jar of peanut butter.
Or a jar of peanut butter, as he does. Shout out to
Professor Dr. Michael
Cordell for physics.
And always having a demonstration for us.
Always having a demonstration. And always having a good attitude. He's always in a good mood. He's always smiling when he comes in. He's got Taco Bell. I mean, he's just a happy guy. And he's a freaking genius. Anyway, and for making Diffie Q easy for people who haven't taken Diffie Q. And then shout out to... She's called that. Shout out to our friend who we won't mention because we didn't ask if he wants to be in the video.
Should we also shout out anyone else in that class?
Shout out to all the people at our recitation table.
That make our lives unique in their own way.
Oh, definitely unique. That's like the best word I would use for what those people make our lives like. That's the adjective I would use. All right, guys. This video is long enough. I doubt anybody's hearing this. But
we'll stop yapping.
We'll stop yapping. Hopefully, this helps somebody. Well, who knows? Maybe someone in 10 years will take this class and they'll look back.
I hope that there is at least someone that is... You know what? If you are watching this video and you are taking this exam on April 22nd, 2025 in Heldenfeld's 200... Know that you are in the same room as us.
With these content creators.
Please come say hi. We might give you an autograph if you ask nicely.
Sure. Yeah.
And maybe we'll smile for a picture.
We may look at you strangely at first and pretend that we don't know who you are.
No, I wouldn't say that.
We're pretty awkward, I would say. Anyway, thank you for watching the video. I hope you enjoyed. If you have any questions, drop a comment. DM me on Instagram at BooberKerns and we can have a chat. All right.